I want you to try a little mental exercise with me, just for a second. Imagine you've been dropped right into the middle of a massive, sprawling corn maze.
Okay.
It's night. You know there's an exit somewhere, and you know there's probably a warm cup of cider waiting for you.
Yeah.
But you have absolutely no idea where to go.
Yeah.
You're at a fork in the path, left to right.
And just to raise the stakes, let's say every single step you take costs you something. You have limited energy. You can't just wander around forever.
Exactly. So how do you find that exit without a map? Do you just pick a direction and hope for the best? That feeling of uncertainty, that need to find a goal, that is the fundamental problem we are tackling today. We're looking at a stack of lecture notes titled Module 3, Informed Search.
And informed search might sound a little, I don't know, dry, like a library system, but it's actually the blueprint for how artificial intelligence thinks.
Right. It's the difference between a Roomba that just blindly bumps into your chair over and over.
And a Mars rover that's navigating a field full of boulders. It's all about moving from, stumbling around in the dark to actually acting with purpose.
And we're going to unpack how machines really find their way. The notes lay out two huge families of these algorithms. First, we have informed search, which is all about the journey, getting those turn-by-turn directions.
And then there's local search, which is where you don't care about the directions at all. You just want to find the best possible final destination.
So like Google Maps versus, finding a needle in a haystack.
That's a great analogy. For the needle, you don't care how you found it. You just want to be holding it at the end.
Okay, so let's start with the informed part. To really get why this is so clever, we have to look at the dumb way to do it first. The notes mention something called uniform cost search.
Uniform cost search is, let's say, the safe bet. Imagine dropping a pebble into a totally still pond. The ripples expand out in a perfect circle. They move in every direction at the exact same speed. That is uniform cost search. It explores every single path outward, step by step, always prioritizing the path that's, the cheapest so far.
Which sounds logical, right? I mean, you don't want to take an expensive step if there's a cheap one you can take.
It is logical, and it's what we call complete and optimal. If a solution exists, this method will find it, and it will be the cheapest path, guaranteed.
Yeah.
But there's a massive downside.
It's just agonizingly slow.
It's so slow because it's blind. It has no sense of direction at all. It will spend just as much time and energy exploring paths that lead away from the goal as it does paths that lead toward it.
It's checking behind the sofa when the exit is clearly the front door.
Exactly. So it's thorough, but it's a huge waste of resources. This is where the notes say we need to give the AI a hint. We need a heuristic.
A heuristic. This seems to be the key.
The heuristic is the MVP of this entire module, really. A heuristic, which we write as one mumble in, is basically a function that estimates how close you are to the goal. It's a compass. It says, look, I can't promise anything, but I'm pretty sure the finish line is about 10 miles in that direction.
The notes use Pac-Man for this, which I love. So if Pac-Man wants to get to a specific pellet, he needs a way to guess how far away it is.
Right, but he can't see the whole maze at once, so the notes suggest using something called the Manhattan distance.
Manhattan distance. Why Manhattan? Is he taking a cab?
It's named for the grid layout of the city. You can't just fly diagonally through buildings. You have to go over a few blocks and up a few avenues.
Oh, right. So you add the horizontal distance and the vertical distance.
Exactly. The absolute difference in X plus the absolute difference in Y.
But the notes make a big deal about this next part. When Pac-Man uses this math, he's basically cheating.
He is. He's solving what we call a relaxed problem.
Which sounds like a good problem to have.
Well, in AI, relaxing a problem just means you delete the rules that make it hard. For Pac-Man, the hard part is the walls.
So to calculate the heuristic, we just pretend the walls don't exist.
We pretend he can just float like a ghost right through them. So the heuristic is him saying, in a perfect world with no walls, it would take me 10 steps.
And even though that number is wrong, because walls do exist, it gives the AI a sense of direction, warm or cold.
Precisely. And that leads us to the first algorithm that actually uses this cheat sheet, greedy search.
Greedy search.
It's very impulsive. It looks at its options, checks the heuristic for each one, and immediately just grabs the one with the lowest number. It always walks toward the goal.
That seems like common sense, though. If I see the mountain peak, I walk toward it. But the notes say this is a flawed strategy. Why?
Because the heuristic is not the real world. It's a guess. Imagine you're driving toward that mountain you see.
Okay.
You're driving straight at it. Greedy search loves this. But then suddenly you hit a giant canyon. There's no bridge.
So I have to turn back. Find a bridge that might be 10 miles east.
But greedy search hates turning back. Moving east means the mountain gets farther away, so its heuristic value goes up. It resists that. It might get stuck in a loop or take some crazy inefficient route. The notes call it fast but dangerous.
So, okay, to recap, uniform cost is too cautious, too slow. Greedy search is too reckless, it runs into walls. We need something in the middle.
We need the gold standard. And this is really the heart of the lecture. A search, or a
Oh,
strat.
that was the famous one. Even if you're not in the field, you've probably used something powered by it.
In video games, GPS routing, logistics, it's everywhere. And it works because it combines the best of both of those other methods using one simple formula, bound Fn plus CAGM Brown.
Let's break that down because this is the core logic. GN is first.
Right, so GN is the backward cost. Think of it like your car's trip meter. It's the actual real cost you have already spent to get where you are now. Uniform cost search only cares about this number.
And that heuristic we just talked about, the forward cost, the estimated cost to get to the goal. Greedy search only cares about this.
Oh, it just adds them together. It looks at the total estimated cost of the entire journey. It asks, how much did it cost to get here? Plus, how much do I think it'll cost to finish?
That's really clever. So if a path looks short, a low $1, but it took me 1,000,000 miles to even get to the start of that path, a high jury.
A would say, nope, that's too expensive overall. It perfectly balances that sunk cost with the potential future gain. And because of that, A is both complete and optimal, but
Oh, I knew there was a but.
there's a catch.
Oh.
A is only optimal if your heuristic behaves itself. Specifically, it has to be admissible.
Admissibility. The notes define it as the heuristic value.
Mm.
Dollar has to be less than or equal to the true cost, which is 1 English.
Or in plain English, the heuristic has to be an optimist. It must never, ever overestimate how much it'll cost to reach the goal.
Why is that so important? I mean, if my GPS says a trip will take 20 minutes, but it really takes 30, that's annoying, but I still get there.
For a human, yes. For A, pessimism is fatal. Imagine your GPS is a pessimist. It looks at a road, and this road happens to be the perfect shortcut, and it says, oh, that looks awful, that'll take an hour.
Well, then I wouldn't take it. I'd take the main road instead.
Exactly. A would prune that option. It would completely skip the best possible path because it was lied to. But if the GPS is an optimist, if it says, this takes 10 minutes, when it really takes 15A, we'll at least try it.
And as it drives, it'll realize, oh, this is taking longer than I thought, and it'll update the real cost.
You've got it. Being an optimist guarantees you don't overlook the best path.
Okay, there's one more layer to A in the notes. Graph search versus tree search. This is about not redoing work, right?
It's all about memory. A basic tree search, it's like it has amnesia. If it walks around the block and ends up at the same corner it was at 5 minutes ago, it treats it like a brand new discovery.
It processes the same state over and over again.
Which is incredibly inefficient. So graph search creates a reached set, basically a checklist of places it's already been. Have I been here before? If yes, we usually just skip it. But, and this is a critical detail, for A, we don't always skip it.
Why not? If I've been there, I've been there.
Because maybe you found a better way to get there this time. Maybe
Yeah.
the first time you took the scenic route, a high cost. This time, you found a shortcut, a lower cost.
So I had to update my records.
Yeah.
Hey, I found a cheaper way to get to this spot.
Exactly. If the new path has a lower route, it's a lower backward cost, you have to update it. Otherwise, you might lock yourself into a suboptimal path.
Okay, so that's informed search. Navigating a maze, counting steps, optimistic compass. But then the notes just take this hard left turn. We leave the maze and enter the world of local search.
This is a total paradigm shift. Up until now, the path itself was the answer we wanted. We needed the directions. But think about a Sudoku puzzle.
Okay, I'm picturing it.
When it's finished, do you care about the order you filled the numbers in? Whether you did the top left corner first or the center box?
No, not at all. I just care that the final grid is correct.
Or the 8 queens problem from the text, placing 8 queens on a chessboard so none of them can attack each other. The sequence of moves is irrelevant. Only that final board configuration matters.
So local search is purely about the end result.
Yes. And because you don't need to store the path, these algorithms use almost no memory. They just look at the current situation and try to improve it.
The most famous version of this seems to be hill climbing.
And the metaphor is surprisingly literal. Imagine you're standing in a really dense fog. Your goal is to get to the highest point in the entire region, the global maximum.
But I can only see the ground right at my feet.
So what do? Well, you check your immediate neighbors. A step north, south, east, west. You feel the ground. And if one step goes up, you take it.
Simple enough? Just keep walking uphill.
Hmm.
Steepest descent.
It's intuitive, but it has a huge, huge flaw. What if you aren't on Mount Everest? What if you're just on a small hill in the foothills?
I'd climb to the top of my little hill, look around, see that every direction is down, and think, I did it. Top of the world.
While the real peak is thousands of feet above you, hidden in the fog. That's called a local maximum. Hill climbing gets stuck there all the time. It
Yeah.
refuses to take a step downhill, even if that's what it needs to do to cross a valley to the real mountain.
And the notes also mention plateaus, these flat areas where the algorithm just wanders around aimlessly.
So how do we fix this? One way is just brute force, random restart hill climbing.
Let me guess. If you get stuck, you just teleport to a random new spot on the map and start climbing again.
Exactly. And if you do that enough times, you'll probably land on the slope of the big mountain eventually. But a much cooler solution is simulated annealing.
That sounds like something from a blacksmith shop.
That's precisely where the idea comes from. Annealing is when you heat metal up and cool it down really slowly to make it stronger. We mimic that process in the algorithm.
So how does heating the algorithm help it find the peak?
Heat is chaos. At the start of the search, we set a high temperature. And this means the algorithm acts, well, erratically. It picks a random move. If the move is good uphill, it takes it. But, and this is the key, if the move is bad downhill, it still might take it.
It accepts bad moves on purpose.
Yes, but it's essential. This bad behavior is what allows it to get off the top of that small local hill. It can stumble down into the valley, which gives it a chance to find the path up the real mountain.
But you don't want it stumbling around forever.
No, of course not. We have a cooling schedule. Over time, the temperature drops. As it gets colder, the probability of accepting a bad move gets lower and lower. Eventually, the system freezes. At that point, it behaves just like regular hill climbing, taking those last few steps to the very top. So you explore a lot when it's hot, and you exploit what you found when it's cold.
It's a really elegant way to avoid getting trapped. Now, there's one last category of the notes that takes this nature-inspired idea even further: genetic algorithms.
Now we're stealing from Darwin. Survival of the fittest, but for data. Instead of one person climbing a hill, imagine you have a whole population of potential solutions.
And for the 8 queens problem, a solution isn't a person, it's just a string of numbers, right? Like 2, 4, 7, 4, 8, 5, 5, 2.
Exactly. Each number is the row for a queen in a given column, so you start with a big population of these random strings. Some are awful, queens everywhere, some are okay.
And how do we decide who survives?
With a fitness function. Here, fitness is just the number of pairs of queens that are safe, that aren't attacking each other. A higher score is better.
And then nature takes its course.
Pretty much. We select the fittest individuals to be parents. Then we take 2 parent strings and do something called crossover.
Yeah.
We just pick a random point, split them both, and swap the tails.
So the kid gets the first half mom's DNA and the second half of dad's.
The hope is that you're combining the good parts of both parents into an even better child.
But if you just keep mixing the same genes, don't you eventually stagnate?
You do. That's why we need mutation.
The X-Men factor.
A tiny bit of chaos. With a very small probability, the algorithm will just randomly change one of the numbers in the string. It moves a queen for no reason at all.
Just to shake things up.
Just to introduce new genetic material. Most of the time, the mutation is bad. But every now and then, that random change is the lucky break that creates a brand new, better solution the parents never would have found on their own.
It's pretty wild. The same logic that evolved life on Earth is being used to solve scheduling problems.
It just shows how powerful the core idea of search is, whether it's logical deduction like A or biological trial and error like genetics. It's all just about finding an answer in a massive space of possibilities.
Before we wrap up, I want to circle back to one term from the A section: dominance.
Ah, yes. This is the pro-level stuff for designing heuristics.
How can one heuristic dominate another one?
So remember, we want our heuristic to be admissible and optimist, but we also want it to be as accurate as possible. If you have 2 different admissible heuristics, and one of them consistently gives a higher estimate than the other without ever going over the true cost, that one is said to dominate.
Because a higher estimate is a more informed estimate. It's closer to the truth.
That's it exactly. If the true cost is 20 miles, and heuristic A guesses 5 miles, and heuristic B guesses 15 miles, B is dominating A. It has better information, and the notes really emphasize this. Better information leads to less search. A will run faster and use less memory with a dominant heuristic.
So the real art for an AI designer isn't just finding any heuristic. It's about finding the most dominant one you can.
That is the holy grail. The sharper your compass, the less stumbling around you have to do.
We've covered a lot of ground today, from the line ripples of uniform cost to the focused beam of A and the chaotic walks of annealing.
It's a whole toolkit, isn't it? There's no single best algorithm for every single problem. You have to know the landscape you're searching.
That's a great way to put it. And it leaves me with one final thought for you to consider.
Mm.
In our own lives, when we're making a decision, are we using A, calculating our past effort plus the estimated future gain? Or are we just hill climbing, just taking whatever seems like the immediate next best step?
And maybe sometimes do we need to accept a bad move, like in simulated annealing, just to get ourselves out of a rut?
Something to think about. Thanks for listening to this deep dive.
See you next time.